Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lecture we have discussed about the interphase mass transfer, the phase equilibrium and other topic related to the phase equilibrium. In this lecture we will discuss about the overall mass transfer coefficient. From the two film theory we know that the individual phase mass transfer coefficient can be obtained easily. We can obtain the individual mass transfer coefficient by using the two film theory, but we cannot obtain the interfacial concentration by using the two film theory because it is difficult to obtain the interface mass transfer. So interfacial concentration are difficult to obtain in real world. So according to two film theory, this is the interface, this is the liquid film, this is the gas film. The component is transferring from the bulk of gas. This is the bulk of liquid. The component is transferring from gas phase. Suppose an absorption case. This is the component A is transferring from gas phase. It passes through the gas film having thickness delta G. Then it passes to the liquid film having thickness delta L. Then it passes to the bulk of liquid. So in the gas phase, in the bulk of gas, the concentration of component A is Ya G at T. At the interface, the concentration of component A is Yai on the gas phase basis, and similarly at the interface, the concentration of component A is the XAI on liquid side, on liquid phase basis, XAI. So Yai and XAI are the interfacial concentration. Similarly, the concentration of component A in the bulk of liquid is XAL. So the mass transfer coefficient in the bulk of the mass transfer coefficient in the gas phase, in the gas film will be Ky. In the liquid film, the mass transfer coefficient is Kx. But in real cases, like in heat transfer, we are using the overall mass heat transfer coefficient. Like in heat transfer, in real world, we are using the overall heat transfer or the overall mass transfer coefficient. For example, in heat transfer, we are using the overall heat transfer coefficient. Suppose in the suppose in the shell and tube heat exchanger, suppose this is a shell and tube heat exchanger. Shell and tube heat exchanger. This is the shell. This is the tube. The hot fluid is flowing through the tube. The cold fluid is flowing through the shell. So it is a shell and tube heat exchanger, a counter flow shell and tube heat exchanger. So in this case, there are resistance to the heat transport. So the one resistance, suppose the hot fluid is flowing through this shell to this tube. First of all, the resistance to the heat transfer will offered by the hot fluid which are flowing in the tube. So the fluid which are flowing in the tube will provide resistance to the heat transfer. Similarly, after this, there will be another resistance to the heat transfer, and this resistance will be provided by the thickness of the wall. So it will provided by the tube wall, and this tube wall will provide another resistance to the heat transfer. So the first resistance which is provided to the heat transfer is denoted by 1 divided by H I. Inside, I is for the inside heat transfer coefficient. Hi is the inside heat transfer coefficient, and 1 divided by heat transfer coefficient is the resistance to the heat transfer. Provided by the fluid which are flowing in the tube side. Similarly, the resistance which is provided by the tube to the heat transfer is denoted by thickness of the tube. Suppose thickness of the tube is delta x, and the thermal conductivity of the tube and the area of the tube. This is the area of the tube, which is 5dl, and K is the thermal conductivity of the tube. Similarly, the cold fluid is flowing in the shell side. So when heat is flowing through the cold fluid, then the cold fluid will also provide resistance to the heat transfer, and this resistance will be denoted by 1 divided by H naught, which is for the outside heat transfer coefficient. H naught is the outside heat transfer coefficient. So there are three resistances which are provided to the heat transport during the shell and tube heat exchanger process. So one is the 1 divided by H naught, one is 1 divided by Hi, another is delta x divided by Ka. If we combine all these three resistance, then we will get the total resistance. And the reciprocal of the total resistance will be equal to the overall heat transfer coefficient. So the overall heat transfer coefficient in the heat transfer, we are using the overall heat transfer coefficient to combine the individual heat transfer coefficient, because sometimes these are unknown to us. So we are using the overall heat transfer coefficient. So during the heat exchanging through this heat exchanger through the tube and shell side will be given by Q, the overall heat transfer coefficient. This overall heat transfer coefficient is nothing but it is 1 divided by Hi plus delta x divided by Ka 1 divided by H naught, which is equal to U, and the area for the heat transport into temperature difference. Now what is the temperature difference? That is the temperature of the hot fluid, which is T1, and temperature of the cold fluid T2. T1 minus T2. So in heat transfer we are using the overall heat transfer coefficient. Similarly, in the mass transfer, by analogy we are using the overall mass transfer coefficient to simplify our calculation. So we are using the overall mass transfer coefficient as we have already used in the heat transfer. So we are using the overall mass transfer coefficient. So in mass transfer, the individual mass transfer coefficient, as we have already obtained from the two-film theory. This is the interface, this is the liquid phase, this is the gas film. The mass transfer coefficient with the liquid film is denoted by Kx. In the gas phase, it is Ky. When we combine the individual mass transfer coefficient, we will get the overall mass transfer coefficient. So the overall mass transfer coefficient on the gas phase basis is capital Ky, and the overall mass transfer coefficient on the basis of liquid phase is the capital Kxo. So when we combine the individual mass transfer coefficients, we will get the overall mass transfer coefficient. So in this lecture, our main focus is on the overall mass transfer mass transfer coefficient. And how can we relate the individual and overall mass transfer coefficient? So in this lecture we will discuss the individual and overall mass transfer coefficient in detail. So we know that at steady state, during steady state, at the interface there is no accumulation of components. So at steady state process, at the interface there is no accumulation of the component in the flux of component A at the interface. Coming to the interface is NA, which is equal to Ky mean the mass transfer coefficient through the gas phase according to full Coulomb theory into Ya G into Ya I. Concentration in the bulk of gas, concentration at the interface will be equal to mass transfer coefficient at the liquid film in the liquid film, XAI concentration of component at the interface on the liquid phase basis, and the XAL concentration of component A in the bulk of liquid is XAL. So at the equilibrium, the flux coming to the interface will be equal to the flux coming out from the interface. So this is the flux coming to the interface, coming into the interface will be equal to flux coming out from the interface. So suppose equation number A. Now we know that it is difficult to measure the interfacial concentration. This is XAI and XAI in the real world because there is no device to measure the interfacial concentration YAI and XAI because the interface are the imaginary plane surface. We cannot take sample from the interface and measure it by using concentration measuring instrument, but we can measure the bulk concentration here in this place and in this place. So we cannot take sample from this interface because first of all it is very thin region, second it is imaginary surface, and the third it will disturb the composition of the other places. So we cannot take sample from the interface because it is imaginary as plane surfaces. So you cannot measure the interface facial concentration. So in this so we will use the overall mass transfer. So we will use the overall mass transfer coefficient and we will use the equilibrium concentration to simplify our study. So Na is equal to Ky overall mass transfer coefficient on gas phase YAG minus YAG star. See the equilibrium concentration of component A in the bulk of gas, and this is the concentration of component A in the bulk phase at the beginning of the process. So it is XAL star equilibrium concentration in the bulk of liquid, concentration of A in the bulk of liquid, concentration of A in the bulk of gas, equilibrium concentration of A in the bulk of gas. So suppose this is equation number 2. Now equation 1. Now we will obtain other equation from equation number 1. Suppose Na here by Ky is equal to YAG minus YAI. Suppose equation number 3. This equation number 3. Similarly, Na Kx is equal to XAI minus XAL is equation number 4. Equation number 4. Similarly, from equation number 2, we can also obtain other equations like Na Na Ky YAG that is equation number 5. Similarly, Na divided by this Kx is equal to XAL equilibrium, concentration of air at the equilibrium minus concentration of air in the bulk of liquid. This is equation number 6. Now from equation number 5, this equation number 5, it consists of the overall mass transfer coefficient on the gas phase basis, and this equation number 3, it shows the individual mass transfer coefficient on the gas phase basis, and this equation number 4 shows the individual mass transfer coefficient on the liquid phase basis. So equation number 3, 4 and 5. From equation number 3, 4 and 5 we will find the relation between the individual and overall mass transfer coefficient. So equation number 3, 4 and equation 3, 4 and 5, we know that Na Ky is equal to YAG minus YAG at the equilibrium. One was this equation, the other equation was Na Ky is equal to YAG minus YAI. The third equation was this is the second equation. The third equation is Na divided by Kx is equal to XAI minus XAL. Now equation number 3. Now take a graphical form and derive and simplify these three equations from the graph. So this is the xy plane. Take the equilibrium. This is the equilibrium curve. This is the bulk point. So point A, XAL. This is the XAL. YAG. Component A in the bulk of gas, component A in the bulk of liquid. Take slope is Kx by Ky. Slope. You will come to the equilibrium. You will find the equilibrium concentration. The equilibrium concentration is come out to XAI and to YAI. We can also find the bulk. This is the equilibrium curve. We come to this point. So the equilibrium concentration of component A in the liquid during the equilibrium, which is XA. L during the equilibrium, XAL star. So this is the, and similarly this point is XAL, which is at equilibrium with gas phase, which is YAG during the equilibrium. So from this graph we will simplify these three equations. So from these three equations we know that YAG minus YAG star this is YAG minus YAG star will be equal to, suppose equation A, this will be equal to YAG minus YAI plus YAI minus YAG. So the interfacial concentration will be cancelled out, and because this is difficult to find, so we can write YAG minus YAG star. It will be written as YAG it will be written as this YAG minus YAG star will be written as, this will be written as YAG minus YAI plus YAI minus YAG star, and this is equal to NA divided by capital K divided by capital K Y, capital K Y. Now from this is equation, suppose equation number A. Now we know that NA divided by KY is equal to YAG minus YAI, which is this term. This term YAG minus YAI is NA divided by KY. So we will put NA divided by KY in this, or in place of this whole term. Similarly, YAI minus YAG. What is the value of YAI minus YAG? YAI minus YAG. YAI is this point, YAG is this point, and this is the y-intercept. This is the y-axis. So suppose we will find some slope. Suppose this is equation. This is point A, this is point B, this is point C, this is point D. Combine point C and point B. A straight line having slope m dash. So this is the y, this is the slope, and the x-axis will be XAI minus XAL. This XAI minus XAL will be the x-axis. So we know that y is equal to mx, so it will be m dash x. This is the slope. So y is equal to m dash x, and x is XAI minus XAL. And we know that what is XAI minus XAL? We know from the previous equation that NA divided by Kx, small kx, is XAI minus XAL. So again in place of YAI minus YAG we will put m dash m2 XAI minus XAL, and in place of this XAI minus XAL we will put NA divided by Kx. So in place of XAI minus XAL we will put NAKX, and we will multiply the slope, so we will get this term. Because this term YAI minus YAG is equal to m dash into XAI minus XAL. Now XAI minus XAL is equal to NA divided by Kx, and if we multiply this NA divided by Kx with m dash, this term will be also multiplied by with m dash, and this is XAI minus XAL, this is XAI minus XAL, and multiplied by m dash, which is equal to YAI minus YAG. So in place of this term, this whole term, we will put NA divided by Kx multiplied by m dash, and in place of this term, we will put this number, and in place of this number we will put this whole number in this place, and this is the Na divided by Ky. So the simple equation is, the final equation is, the final equation will become Na divided by Ky, capital Ky is equal to Na divided by Ky, this is the capital Ky, plus m dash, slope of the line, and this is the Na to x1. So this is the small kx, small ky, capital Ky. This cancel with this, it is 1 divided by Ky, capital Ky, is equal to 1 over Ky plus m dash Kx. So this equation is the final equation. This equation is the final equation which shows the relation between the overall mass transfer coefficient on the gas phase to the individual mass transfer coefficient on the liquid and gas phase. So in this equation, suppose this equation number m. So this equation m shows us relation between the overall and the individual mass transfer coefficients, and it shows that the resistance provided by the gas phase plus the resistance provided by the liquid phase, when combined, it will give us the overall resistance provided by the liquid and gas phase to the mass transport. So this is the overall resistance. These are the individual resistances. So the overall resistance and the individual resistances. The overall resistance is 1 over Ky and the individual. So the resistance provided by the gas phase will be equal to 1. The fractional of resistance provided by the gas phase will be equal to 1 divided by Ky divided by 1 divided by capital Ky. This is the fraction of resistance provided by the gas phase. Similarly, the fraction of resistance provided by the liquid phase will be equal to 1 divided by Kx divided by the overall resistance. So this is the fraction of resistance provided by the liquid phase, the fraction of resistance provided by the gas phase. Similarly, we can also obtain another equation which relates the overall liquid phase mass transfer coefficient to the liquid and gas phase mass transfer coefficient. So we know that Na is equal to Kx XaL at the equilibrium minus XaL. So we can suppose this equation number equation 1. Similarly, we also know that Na is equal to Kx Ky Yag minus Yai. We also know that Na is equal to Kx Xai Xal. Equation 2, equation 3. Now simplify equation 1. We will get Na by capital Kx Xal minus Xal. So now this Xal at the equilibrium minus Xal will be equal to this Xa star XAL star minus XAL will be equal to XAL star minus XAL will be equal to XAL this will be equal to XAL star minus XAI XAL star minus XAI plus XAI plus XAL. XAI minus XA should be minus 1 minus XA minus XA. This is the XAL minus XAI plus XAI minus XAL. Now, what is the XAL star minus XAI? So again it can be obtained from the from a line. So put D and combine D and B by a line. So we combine point D and point B by a line having slope m double dash. So again this is the slope of this line which combine point D and point B. So again the y-axis is YAG minus YAI. This is the y-axis, YAG minus YAI. The x-axis is XAL star minus XAI. The x-axis, and the slope is m double dash. So XAL star minus XAI is the x-axis, and we know that y is equal to mx. So it will be, the x-axis will be equal to y divided by slope, and slope is m double dash, and what is the y-axis? Y-axis is YAG minus YAI. YAG minus YAI, and YAG and YAI from equation number 2 from this equation is YAG minus YAI is NA divided by KY. So again this is the NA divided by KY, y-axis, and the y-axis is equal to NA divided by KY, because YAG minus YAI from this equation and from this graph is equal to NA divided by KY and divided by slope, and the slope is nothing but it is the m double dash slope of this line. So m double dash plus XAI minus XAL. Now from equation number 3, this is XAI minus XAL, it is equal to NA divided by KX. NA divided by K, small kx. And again it is equal to NA divided by capital KX. NA this. So again this is the relation. Again this equation shows the relation. This equation shows the relation between the individual and overall mass transfer coefficient on the liquid and gas phase basis. So this equation can be written as 1 divided by Kx is equal to 1 divided by Ky m double dash plus 1 divided by Kx. So again this is the total resistance, these are the individual resistances. So 1 divided by ky and double dash divided by 1 divided by kx. This is the total resistance. This is the resistance provided by the gas phase. So the frictional resistance provided by the gas phase and the is equal to 1 divided by ky into m double dash divided by 1 divided by kx. Similarly, the fractional of resistance provided by the liquid phase divided by kx divided by the overall resistance. So these resistances are very important in the absorbing of gases in the liquid. Some gases are very soluble in the liquid, some gases are strongly soluble in the liquid, some gases are insoluble in the liquid. So if a gas is soluble in the liquid, its mean that the only resistance is provided by the gas. If a gas is very soluble in the gas phase in the liquid, then what will be it mean? It means that it will be the only resistance will be provided by the gas phase to the component transport. So the only resistance will be provided by the gas. So what will be the previous equation? The previous equation was 1 divided by ky is equal to 1 divided by ky L dash kx. This was one equation. Equation star. What was the other one? M double dash divided by m double dash divided by kx m double dash divided by m double dash m double dash sorry, this is the yag minus ya yag minus ya which is nothing but 1 divided by k y into m double dash plus divided by k. This is equation b dash. So these two are very important equations which show a relation between the individual and overall liquid and gas mass transfer coefficients. So some gases are very soluble in the liquid. For example, ammonia is very soluble in the liquid, so the only resistance will be provided by the gas to the transport of ammonia. So only gas will be provide resistance to the, so this component will be very, this will be not this part will be not negligible and this part will be negligible. So in this case, in case of ammonia, 1 divided by ky will be approximately equal to the 1 ky. Similarly, if the gas is not soluble in the liquid, then very high resistance will be provided by the liquid to the gas transport. So this term will be negligible and this term will be very high. So 1 over ky will be equal to m divided by kx. So this is all about the individual and overall mass transfer coefficient. So if you are new to the channel, please like and subscribe. Thank you very much.